We should be, hold on. All right, all right, all right, all right. Okay, so let me share my screen. And today we're going to start with chapter 7, which deals with the atomic structure. And again, some of what we're going to cover, you should have encountered before in your introductory chemistry or high school chemistry. But what you're going to find is that we're going to delve into things a bit more deeply. So some things, especially in terms of quantitative calculations and so on, you would not have met before. So this will be new to you. All right. So let's talk about the atomic structure. And just a brief overview of how we come to our current understanding of the structure of atoms, especially with respect to how the electrons are arranged. So way back when, and I don't exactly know what the year was, but back in the day, people used to believe that particles like electrons basically behave the same way as regular sized objects, right? So basically, the belief was that they behave according to what is described by the laws according to Newton. And then some experiments were done with light. We're going to describe some of that shortly, which leads us to a theory known as a quantum theory, which has a more accurate description and representation of how small particles like electrons behave. So that leads us to what is called the quantum view, which describes the behavior of electrons in atoms. And we're going to look into that behavior not only in this chapter, but in the next chapter as well, chapter 8. All right. So let's talk about how the electrons were discovered. Now, I'm going to show you a diagram which led to the discovery of the electrons, right? Now, if you have this setup right here, and this is an experiment that was carried out by this guy, Johann Hittorf, in 1869. And basically what he did was that he had a tube here, which was evacuated. So this part of the tube was connected to a vacuum pump. So there's no air inside here. You have two electrodes. Both electrodes are connected to an electricity source, right? So this electrode is the cathode, it's negative, and this electrode is the positive electrode known as the anode. So when the switch is closed, what happens or was observed was that a stream of particles was observed emanating from the cathode and moving towards the anode. All right. And this was something new. And as always happening in any scientific endeavor, whenever there's a new discovery of anything, then the scientists will basically rush to try to play with this to see, what features or what new discoveries can arise from it. And that is no less true for this discovery, right? Based on just this experiment alone, the conclusion can be arrived at that the particles are negatively charged, right? Because they emanate from the cathode, which is negatively charged, and are attracted to the anode, right? So that's basically pretty much the only conclusion that can be arrived at based on this experiment. So other people started doing modifications of this experiment to see what the nature of these particles are, apart from the fact that they're negatively charged. So what was discovered, for example, was that the rays that they were called cathode rays, which is a stream of particles, can be deflected by the presence of a magnetic field and also by an electric field. So as you can see in this replica of the same experiment, same thing happens. You have a stream of particles produced by the cathode, but because of the presence of this magnet right here, the stream of particles are deflected downward towards it, right? And something similar will happen if this was done in the presence of an electric field, right? The particles will deflect to the positive part of the electric field, right? Some other things that were observed about these rays is that they cause glass and other materials to fluoresce, which basically means that they light up. So when the rays hit the glass particles or whatever the material is, it lights up, right? And as I said before, it is deflected by a magnetic field. Okay, so this guy, J.J. Thomson, he decided to investigate this some more. So he made some modification to the original experiment. As you can see here, it's a bit more sophisticated. It still has the cathode here and the anode here, which is connected to the external circuit, right? But in addition, there's another piece of material right here, piece of metal, which has a slit. And also the anode here has a slit as well. So when the cathode produces the stream of electrons, it forms a beam as it emerges from these two slits, and then it is led into this area here. Now, in this area, we have two magnets, right? And we also have two plates, which are themselves connected to an external circuit, right? So what J.J. Thomson was trying to do was to see how the stream of particles are deflected when you vary the magnetic field and also vary the electric field, right? And he has a scale here which basically measures the angle of deflection, all right? So that's basically the setup. So he did some calculations, and for those of you who are going to do physics, or if you have done physics already, you will get into this in more detail because I remember doing that when I was a student. I minored in physics, and I remember we looked at the calculations involved. I won't go into all that right now. Basically, the result of this experiment was that J.J. Thomson was able to find the mass to charge ratio of the particles, which we now call electrons, right? And this is what he ended up determining. The mass to charge ratio of the electrons is equal to minus 5.686 times 10 to the minus 12 kilograms per coulomb, all right? So that was a major step in terms of understanding the nature of these particles, all right? However, of course, scientists are not satisfied with that because while it's important for us to get the mass to charge ratio, we really do need to find the mass and the charge separately, right? So other people start doing their own thing in terms of further investigation of the nature of these particles. And this guy by the name of Millikan, oh, by the way, before I mention that, as you can see here up here, Stoney, he's the one who is credited with the term electron to describe these particles, all right? Millikan, he came up with his famous oil drop experiment. And again, this is something, if you have to do physics or if you have done physics, then you would have met this experiment and you'd have been familiar with the calculations associated with it. Again, I won't go into all the calculations, but let me just qualitatively describe what is happening here. So basically, in his setup, he has this apparatus where you have two plates, two metal plates. This one is the cathode. This one is the anode. They're both connected to an external circuit. And you have a hole, a very small hole, in the case of the cathode, right? Now, here we have some oil. I don't remember exactly what kind of oil it was, but basically, you have a contraption here which allows you to spray a fine mist of oil droplets, and the oil droplets will eventually, some of them will eventually find themselves through the hole and will end up in this region right here. Now, once in this region here, it will be impacted by a source of ionizing radiation, right? So you have some radioactive material here that will produce radiation, and the role of the radiation is to knock off electrons from the oil drop, all right? So basically, the oil drop, as a result, when electrons are knocked off it, becomes positive. And if the electric field between these two plates are at the right value, then you can suspend the oil drop between them, right? So the oil drop will actually suspend in air between those two electrodes. Based on that suspension, we can conclude that the force of gravity that is acting on the oil drop down, going downwards, would be equal to the electrical force, which is responsible for pulling the oil drop upwards, right? So based on those two facts, then we can do some calculations. And based on the calculations that were done, Millikan was able to determine the charge on the electron, and this is what he determined. The charge on the electron is equal to minus 1.602 times 10 to the minus 19 coulombs. Excuse me. I don't know if you're familiar with this unit of coulomb. Oh, I can't do that. Okay, hold on. Um, uh, okay, so the Coulomb unit is basically a unit of charge, all right? Again, for those of you who have to do physics, you're going to meet this um, later on, all right? So that's the unit of charge. Okay, so based on the value of the charge on the electron and based on the mass to charge ratio, right? In order for us to get the mass of the electron, all we have to do is multiply this mass to charge ratio by the charge on the electron, and that will give us the mass of the electron. And therefore, we now know that the mass of the electron is what you see here, which is 9.109 times 10 to the minus 31. All right? So that's basically how we now arrive at knowing the nature of these particles. All right? All right, so let me clear this. And let's talk about how the electrons are arranged. And not only electrons, but the other particles as well. So another scientist by the name of J.J. Thomson, who, by the way, was a student of the one I mentioned before, he propose that the way the particles are arranged in the atom is that you have the electron, which is embedded in a large positively charged region, right? Relatively speaking. And the electrons are equally spaced in that positively charged sphere, right? So that was the proposal that Thomson came up with, all right? Um, because by then it was known that we have particles known as electrons, and we know that there's another part of the atom that was positive, right? That's all that was known back then. So he came up with this idea based on that information, all right? So, for example, his proposal for the hydrogen atom is that you have one electron, and that electron is right in the middle of the positive sphere. And in the case of helium, you have two electrons, and those two electrons would be on a straight line right through the center, and the electrons would be basically evenly distributed halfway between the center and the outer sphere of the outer surface of that large positive sphere, right? So just to give you a pictorial representation of the helium atom, according to J.J. Thomson, right? This is basically what he was suggesting, right? You have the large positive sphere, which has a total of 2 plus charges, and the electrons each will have a negative charge, and this is how they're distributed evenly within that large positive sphere, right? And what he suggested also is that if you were somehow able to remove one electron from here, then the other electron will simply move to the middle, and you're going to end up with this arrangement, right? So in some textbooks, they call it the raisin pudding model, right? Basically a description of how the electrons are embedded in the large sphere. So that was the model that was put forward by J.J. Thomson, right? So of course, in the scientific method, right? If somebody put forward a model, then either that person or another person would investigate to see if that model works. So therefore, it would be subject to testing. So another scientist by the name of Rutherford, let's see if I can get to the next slide. He, by the way, was a student of J.J. Thomson, and he came up with his famous gold leaf experiment, right? So let me try to describe basically how this works, right? So what we have here is your metal foil, which is gold, actually, right? A very thin sheet of gold. And he basically bombarded that gold sheet with alpha particles. Now, alpha particles, just to let you know, alpha particles are helium nuclei, helium-4 nuclei, I should say. So this is basically what alpha particles are, all right? So this is positive, right? And basically what he was testing to see if the plum pudding model works is that if you shoot alpha particles at that metal foil, because most of the atoms would be positive in terms of the size, then you'd expect that the alpha particles would be repelled. So therefore, they will be turned back, right? So that's basically what we're looking for if you're trying to test this particular model, right? So what Rutherford did was he carried out this experiment, and what he discovered was that, to his surprise, that the particles did not all the particles were turned back, right? Some of them, in fact, most of them, passes right through the gold metal foil. Now, some of them are deflected at an angle, as shown here, and shown here, and some of them are repelled as well, as shown here, right? But the vast majority of the particles passes right through the gold foil and is detected by the detector on this side right here, all right? So therefore, this contradicts the plum pudding model, and Rutherford came up with his own model to explain this observation. And according to his model, which is more closer to what we know to be the truth right now, according to his model, the bulk of the size of the atom is taken up by the electrons, which are surrounding the the nucleus, which is very small and very dense, right? And is positively charged, all right? So that explains that observation as shown in this diagram right here, because since the electrons are spread out and diffuse, then most of the alpha particles will simply pass right through, as shown by pathway 1 here, pathway 1 here, pathway 1 here, and so on and so forth. For all the pathway ones, they basically go in a straight line passing right through the atom. Now, you have a few of the alpha particles which approach closely to the nucleus and are deflected, such as the pathway here, number 3, the alpha particle comes here, and then because the alpha particle is positive and this is positive, then it deflects going in that way. And then if you look at pathway 4, this is an example of one of the situations where the alpha particles comes into direct contact with the positively charged nucleus and then is directed in the opposite direction, all right? So this basically is the interpretation according to Rutherford, which makes sense based on what he observed in his experiment, all right? Now, so far, up to this point, the electrons and protons were basically discovered, all right? Rutherford, that is, was able to determine the amount of positive nuclear charges, and these are carried by particles which we now call protons, right? So we know of the electrons. Based on Rutherford's experiments, we also know of the protons, but there was an issue back then because what was determined or what was found out was that for the atoms, the total mass of the atoms could not be accounted for by simply just looking at the masses of the protons and the electrons. So therefore, there is a missing, what's the word I'm looking for? Missing particle, so to speak, that was not yet discovered, which contributed to the total mass of the atom. And a guy by the name of Chadwick, oh, by the way, the atomic number, that definition arose from the fact that we now know the number of protons, right? The number of protons would be the atomic number. Chadwick, this guy, who, by the way, was a student of Rutherford, he discovered the neutrons. I won't go into the experiment that he conducted to discover that, right? But he discovered the neutrons because, as I said before, there was a mass difference that could not be accounted for until he discovered the neutrons, and that explains that difference in mass that exists in most of the atoms, right? And he discovered that the neutrons, these particles, have no charge, and their mass is almost the same as the mass of a proton, all right? So that's basically a short history of how these particles were discovered. Okay, let me clear this here to avoid any confusion. So let me talk about mass spectrometry. Now, mass spectrometry is basically a technique which is used to determine the different isotopes of an element, all right, based on their different masses. As you all know, isotopes are elements which have the same number of protons, but their mass numbers are different, and therefore their masses are different, all right? So basically, the mass spectrometer, which is the instrument used in this exercise, is basically used to separate the positive ions of the element according to their mass to charge ratios, all right? So let me show you what is called a mass spectrum, which is a record of the separation of the ions, right? So I think, if I'm not mistaken, this is the mass spectrum for the helium atom or the helium element, right? So if you look at this here, this is a plot of the relative number of atoms versus the mass to charge ratio. And basically, you'll notice that the helium atom, which has the greatest abundance in terms of the relative number of atoms, is the one that has a mass of 202, all right? And then the next in line would be the one with 200 mass, and then 204, and so on, all right? So this is called a mass spectrum, okay? Now, how do we get this record? Well, as I said before, the instrument that is used is called a mass spectrometer. And the way this works is that firstly, you'd have to convert the element into a gas if it's not a gas already, all right? So mercury is a liquid, so what you have to do is vaporize it, and then what you have to do is bombard it with some electrons, and that will convert those atoms into ions, right? And then you allow it to pass through a region where you have a magnetic field. Now, the effect of the magnetic field on the ions is that it's going to make sure that its pathway deviates from a straight line into a kind of circular pathway. And what you'll find is that the lighter elements will have a smaller radius in terms of the pathway, and then the heavier the isotope, the greater will be the radius of the pathway, all right? So based on the different radii of the pathway for the different ions, that causes a separation of those ions according to their masses, and therefore when they hit the photographic plate, you're going to get a record where the most intense line would represent the isotope of greater abundance, right? Which would be the isotope where the mass number is 202, all right? So that's basically how the mass spectrometer works. And for those of you who have to do organic chemistry, you're going to see the role of mass spectrometry in terms of determining the structure of organic molecules, all right? But this is just an introduction to how it works, all right? So as stated here, the lightest ions will be deflected the most and therefore would have a smaller radius in terms of its journey towards the photographic plate. And that's the basis for the separation of the different isotopes. Okay, so moving along. Okay, so now we're going to talk about wave motion. Now you might be wondering, why in the world would we be discussing wave motion at this juncture? Well, as you're going to see shortly, understanding wave motion will be key to understanding how the electrons are arranged in the atom, all right? So you might not see the connection now, but I'm going to make the connection shortly. But trust me, it's very important that you understand the nature of the wave and the different properties of a wave, all right? So I'm quite sure we have all had the experience as kids where you have a rope attached to a fixed wall or something, and you hold the other end of the rope and you move it up and down, right? And by so doing, you create a wave that is traveling along the rope, all right? Now, of course, we all know that the particles of the rope are not moving along the length of the rope. The particles of the rope will be moving up and down, but the energy generated by moving this end up and down creates the waveform that is transmitted along the length of the rope. So, understanding different properties of the waveform in this situation will become important when it comes to understanding the waveform in electromagnetic radiation that we're going to discuss shortly, right? As stated here, the wave is characterized by several things. One of them would be the height of the crest or the depth of the trough, all right? Now, as I said before, excuse me, the nature of the wave that I just described on the previous slide is very similar to the nature of the wave that's associated with light and all forms of electromagnetic radiation, all right? So electromagnetic waves, which among which light is a form of EM waves, originate from the movement of electric charges. And this diagram here shows you basically how that works. So imagine that this is a beam of light going in this direction, all right? So you're going to have at right angles to each other, the electric field component, which would be described by this pink waveform right here. And then you have the magnetic field component, which is described by the black and blue waveform, which is perpendicular to the first one. All right. So basically, you have basically identical waveforms which are perpendicular to each other, right? So that's basically what is makes up all forms of electromagnetic radiation, including the light that our eyes are sensitive to. Okay, so let's talk about the different characteristics of the waveform. The first of which is what is known as the wavelength, right? The wavelength is the distance between any two identical points in consecutive cycles. In some textbooks, they may say that the wavelength is the distance between two successive peaks or two successive troughs, all right? So that's the wavelength. And the symbol that is used in almost every literature to represent wavelength is this Greek letter known as lambda, looks like an upside down Y, all right? So lambda is the wavelength, and the wavelength literally can be expressed in any unit of length, right? Could be meters, centimeters, whatever, all right? So that's one important property of a waveform. The other important property of a waveform is what is known as a frequency. Now, the frequency of a wave is the number of cycles of the wave that passes through a point in a unit of time. And usually the unit of time would be seconds, right? So let me just put here in parentheses seconds, right? So the units of frequency, unit of frequency is seconds to the minus one. And there's a special name given to that unit. It's called the hertz. All right? So that's the hertz unit. Okay, so that's a frequency. That's another characteristic of the waveform, all right? Of any waveform, including electromagnetic waves, all right? So that's that. And then the third property of a wave is known as the amplitude. And the amplitude of the wave is basically the height of the wave above the line of no disturbance. So basically, if you draw a line from the line of no disturbance through the center of the wave peak, then that is the amplitude. All right, so those are the three main characteristics of a wave. Now, two of these characteristics are related to each other directly. And basically, this equation shows you that relationship, right? The speed of the wave, right, is defined as the frequency multiplied by the wavelength, all right? So if the frequency is in seconds to the minus one, if the frequency is expressed in seconds to the minus one, and the wavelength is expressed in meters, then the unit of the speed of the wave is ms to the minus one, or m over s. All right. So that's a relationship between the frequency and the wavelength, right? The wavelength times the frequency would give you the speed of the wave. All right. Okay. So that's the relationship between those two, which will become important as well when it comes to electromagnetic radiation. In fact, oh, I think I have the slides out of order, so I apologize for that. Let me move on to the next slide, because the next slide, let me clear this here. The next slide is a statement about electromagnetic radiation, right? All forms of electromagnetic radiation show wave-like behavior, and also true is that all form of electromagnetic radiation travels at the same speed, and that speed is given right here. C is equal to 3.00 times 10 to the 8 meters per second. That is true for all forms of electromagnetic radiation, including the speed of light, all right? So going back to this equation here, basically all we have to do is set this to be equal to C. So this will be equal to C in the case of electromagnetic radiation. All right? So what that means is that there's an inverse relationship between the frequency and the wavelength, right? So the longer the wavelength, the lower would be the frequency and vice versa. All right. Now, let's talk about this slide right here. This slide basically shows you the full listing of all forms of electromagnetic radiation. We call this the electromagnetic spectrum, all right? And the way it is arranged in this diagram is that we start off on this side with the highest frequency radiation, and the frequency decreases as you go from left to right. Correspondingly down here, the wavelength would start off small and then increase going from left to right. Because again, of the inverse relationship between frequency and the wavelength. So if you start from this end, in terms of the high frequency radiation, you have the gamma rays, X-rays, right? And then you have what are known as the ultraviolet rays, okay? And then there's a narrow band here. This is where you'll find the different colors of light, all right? Which starts with violet and goes through different transitions until you get to red. In fact, there is a memory tool that you can use, well, that I use to remember the order of the colors in terms of increasing frequency, which would be Roig-Biv, right? Red, orange, yellow, green, blue, indigo, violet, all right? So that gives you the order of the different colors in terms of increasing frequency, all right? Which means that the wavelength would increase in the other direction, increasing wavelength. All right? Okay, so that's the narrow band right there. And then beyond that, you have the infrared region, then you have microwave, and then you have the different radio waves like TV, FM radio, AM radio, cellular phones, and all that. And then at the extreme low end in terms of frequency, you have what is called the extra low frequency type of radiation, all right? So as stated down here, the vast majority of the electromagnetic spectrum is invisible to the eye, and therefore, in order for you to detect all those different types of radiation that we can't see, you'd have to use some instrument in order to detect them. The only part of the spectrum that our eyes are able to detect is the visible region right here, which is this narrow band, all right? Okay, so that's basically the electromagnetic spectrum. Okay, okay, we saw this before. Before we get to that, let us look at some questions from the assignment for this chapter. Let me clear this here, and let me get out of this. And let me minimize this here. And let me go here and close this out. Okay, and then go to this here, assignment. And okay, so I'm going to publish this now. And let me open this up, because I think now we should be able to do some problems from this assignment. Okay, so let's look at question 1, which says, an FM radio station broadcasts at 95.5 megahertz. Calculate the wavelength of this corresponding radio waves, all right? So remember the equation that I just introduced to you, which relates wavelength to frequency, and that is C is equal to lambda times nu, all right? Lambda is the wavelength, nu is the frequency, C is the speed of light. And remember also that C is constant, 3.00 times 10 to the 8 meters per second, all right? So let's apply this to this question. The question gives you the frequency, right? Oh, by the way, remember I said also that the frequency can be expressed in hertz, all right? The wavelength can be expressed in many units, but in this particular case, we're going to use meters, all right? So The question is asking for us to calculate the wavelength, right? So we need to calculate lambda. So based on this equation, we can say that lambda is equal to C over nu. Now C, as I said before, is 3.00 times 10 to the 8 meters per second, divided by the frequency. Now the frequency is given as 95.5 megahertz. Now, mega means 1 million, right? So what we have to do, because remember now, hertz is the same thing as seconds to the minus 1, which we have here. This is seconds right here, right? So what we have to do is convert megahertz to seconds to the minus 1. And basically, that would be 1 megahertz down here and 10 to the 6 hertz, which is the same thing as 10 to the 6 seconds to the minus 1. So this will go with this will go with that, and you're going to end up with your answer expressed in meters. So when I do the calculation, 3 times 10 to the 8, 3 times 10 to the 8, divided by 95.5 times 10 to the 6, according to my calculation, and please correct me if I'm wrong, but according to my calculation, I got 3.14 meters, rounded off to 3 sig figs, all right? And that's basically how you would do that problem, all right? Okay, any questions about this one? Any questions? Any questions? Okay, so let me clear this and scroll down. Okay, number 2. All right. We should be able to do number 2A, but not B yet. So let me let's do number 2A. Now, in the case of number 2A, they gave us the wavelength, 7.80 times 10 to the 2 nanometers, and the question is asking for the frequency. All right? So in this case, the frequency nu will be equal to C over lambda. So nu would be equal to 3.00 times 10 to the 8 meters per second, divided by the wavelength, which is 7.80 times 10 to the 2 nanometers. But we have to convert nanometers to meters because we have the meter unit up here. So nano means 10 to the minus 9. So that means that 1 nanometer here will be equal to 10 to the minus 9 meters. All right? And that's the setup. So all you have to do now is do the cancellation of units. And then your final answer would be expressed in seconds to the minus 1 or hertz. So let's see what that gives. 3 times 10 to the 8 divided by 7.80 times 10 to the 2. And according to my calculation, I got, rounded off to 3 sig figs again, 3.85 times 10 to the 14 seconds to the minus 1. And that's how that is done. All right? Okay, any questions about this one? Any questions? Any questions? Okay, so let me go back to the PowerPoint because we cannot do B right now. So let me get rid of this first. And let me switch over to the PowerPoint. Okay, okay, what's going on here? Oh. Okay, where is the thing for the PowerPoint? Okay. All right, so let's continue our discussion. Now we're going to talk about what is called the continuous spectrum. Now, if you take white light, right, and you set up this experiment where the light emanating from your light source is allowed to pass through a slit, which is allowed to pass through this prism. Now, this prism here can be made up of any material that's transparent, like plastic or glass, right? So the light passes through. What's going to happen is that the different colors of light that makes up the white light will be refracted. Let me write that term down here. We call this refraction. Again, if you're going to do physics, you're going to meet this term, right? Refraction basically is the bending of light as it passes from one medium to another. So let me just say this is the bending of light as it passes from one medium to another. All right? So basically, the different colors of light will be refracted to different extents, and therefore you have the different colors separated on that basis. So the refraction will take place here, and then another refraction will take place here, and then that light will be projected onto a screen, and you end up with what is called a continuous spectrum, right? Which is basically all the different colors of light, and you'll notice it's continuous, which means that basically as you go from one end to the next, basically the colors run into each other. There's no clear separation between the red and the orange and the yellow and so on, right? Basically, they just merge into each other as you go from one end of the spectrum to the other, all right? So we call that a continuous spectrum. Let me clear this here so we can see what that is saying. Okay, so basically it's just saying what I just said, all right? So that's what we call the continuous spectrum. And this is basically the same thing that you would see in the rainbow, right? Basically, the rainbow that you see outside is due to water droplets refracting the light from the sun and separating the different colors, and you end up with the rainbow, all right? So, the different colors of light, of course, correspond to different wavelengths and frequencies. So as you can see here in this diagram, the red light, its wavelength is approximately 650 nanometers. The orange is approximately 575, and so on and so forth, all right? So those are the different colors associated with the different wavelengths and, of course, the different frequencies. So that's the continuous spectrum. Now, there's a different type of spectrum that can be produced if you have a setup as shown here. Now, what is shown here is what is called a hydrogen lamp. It consists of a tube which has hydrogen at a very low pressure, right? And at each end of the tube, you have electrodes, which is connected to an external circuit. So when you flip the switch on, you get this pink colored light. You allow it to pass through the slit, and then it hits this side of the prism, emerges on the other side, and projected onto the screen. And what you end up with is a spectrum where you have lines of a particular color being displayed. I don't know if you can see it on your end, but here we have, this looks like a red line. This looks like it's blue, and this looks like it's purple or indigo violet. I can't tell the difference between those colors. In fact, I remember reading somewhere that only women or females can tell the difference between indigo and violet, which is probably true because I can't tell the difference between those two colors, all right? So that is what is called a line spectrum, right? And what you'll find is that if you substitute hydrogen with different elements, you're going to get different line spectra, right? In fact, each element will have its own unique line spectrum. So in other words, you can look at the line spectrum of, let's say, an unknown element and compare it to that of the known element. And if it's the same, then you know it's the same element, all right? So that's basically used to identify different elements. In fact, I think the next slide here, let me see, yes, has the line spectra of different elements. So this is for mercury, this is for lithium, this is for cadmium, and strontium, and so on. And this is called an atomic emission spectrum. And astronomers, people who look at, celestial bodies like suns and stars and so on, this is what they use to identify the fact that there are different elements present, for example, in the sun, all right? They have their own special instruments, and somehow their instruments are designed to basically separate out the different spectra for the different elements. And by so doing, you can identify, for example, that iron, which is a solid element down here on Earth, exist as a gas up there in the sun, for example, all right? So this is treated as a fingerprint for the different elements. Okay, now let's talk about what is called black body radiation. And this is basically based on an idea that was put forward by a German scientist by the name of Planck. And he proposed that if you have vibrating atoms in a heated solid, they would absorb or emit electromagnetic energy in only discrete amounts, right? So basically what this suggests is that the energy change by unique, discrete, what we call packets, or I should say quantum, right? So the smallest amount of energy, quantum, is that packet which an atom will either absorb or emit. And there's a formula that is used to calculate the energy of that quantum. It's called, or it's a formula is E is equal to h nu. H is known as Planck's constant, which is given right here, 6.626 times 10 to the minus 34 joules second, right? For our purposes, we'll just round this off to 6.63 times 10 to the minus 34 joules seconds, all right? So that's basically how we calculate the energy of these packets of radiation, okay? So according to Planck, the energy of an object will be changed only as a quantum, which is given by this formula, or whole number multiples of a quantum, all right? So this leads us to basically what is called a wave. Let me write it here. In some textbooks, you see they call it a wave-particle duality of radiation. Wave-particle duality of radiation. And what this means basically is that in some respects, radiation behaves like a waveform as we described before, but based on what Planck was discussing here and what is observed experimentally, radiation also displayed particle behavior, right? So we have these two things basically going on as far as radiation is concerned, right? And I can imagine, and I'll understand that you might have difficulty appreciating this fact. All I can say is that all evidence point to radiation behaving as a wave as well as behaving as a particle. All the evidence basically point in that direction, that there's this duality that exists as far as radiation is concerned, right? So that's that. So let me move on now to the next slide. Let me clear this first. So I want to talk about one aspect of this, and that is the photoelectric effect. And I'm going to show you this diagram right here, which show you an experiment. Okay, so in line with what Planck discovered, Einstein came up with the term photons, right, to describe the packets of energy, right, packets of electromagnetic energy, right? So that's basically the term that we're going to use from now on to describe these packets. Okay, so let's talk about this experimental setup. What we have here is two electrodes encased in this glass encasing right here. We have one electrode, which is this pole right here, is an anode, and this electrode here is made up of a photoemissive material. I don't remember what the material is, but basically this material here will emit electrons if it's exposed to radiation of the correct frequency, right? Both electrodes are connected to an external circuit, and as a part of this external circuit, you have this instrument known as an ammeter, which basically detects an electron flow going through the external circuit, right? So when the photoemissive material is exposed to radiation, as I said before, it basically liberates electrons, and these electrons would migrate through the air from the cathode to the anode, all right? And thereby an electric current would be detected, all right? Now, remember this formula here. That's the energy of the photon, right? What was determined based on the experiment is that only photons with a particular frequency above a certain threshold value will cause an electric flow, right? So what we're saying here is that if the frequency of the photon is below a minimum, or I should say a minimum value, right? Then there'll be no current that would be detected. And that is shown in this diagram right here. On the y-axis, you have the current flow. On the x-axis, you have the frequency of the light. If the frequency of the light is below this threshold frequency, then there'll be no current flow. Once you get to that threshold frequency, then basically you're going to get current flowing, all right? And again, this is something that you're going to meet in physics. There's a thing called work function, which is basically the energy required to liberate the electron from the photoemissive material. And that work function is basically related to the threshold frequency. I won't go into all that because that's for physics and not chemistry. Also very important that you realize is that the flow of the current is not in any way dependent on the intensity of the photon. In other words, it doesn't depend on the number of photons that is bombarding the photoemissive material, right? So it doesn't matter if the intensity is low or high. If the frequency is not the right frequency, then there's no current flow that will be observed, all right? Okay, so that's the photoelectric effect. Now, let's relate what we have just discussed in terms of radiation and photons and all that to the structure of the atom. And this guy, Niels Bohr, he came up with a model of the hydrogen atom based on, in part, all that we have discussed so far, right? So he did some theoretical work. Again, I won't go into all the details of that. I'm just going to give you the conclusion that he arrived at. He arrived at the conclusion that the electron energy in the atom is quantized. And what that means is that the electrons can only have a certain fixed value in terms of its energy, right? As long as it lies within a particular orbit, right? So according to the Bohr model, you have the this arrangement where you have the nucleus in the middle, you have the electrons traveling in basically different definite orbits, right? So you have this orbit here, which is designated n equal 1, and then you have the n equal 2 orbit, you have the n equal 3 orbit, and so on. While they are occupying their respective orbits, the electron will have a certain amount of energy. And he actually did some calculations, and he came up with an equation which gives you the energy of the orbit, and that's this equation right here. En is equal to minus RH over n squared, where n is the n value for the orbit as shown here, and RH is a constant, which is known as the Rydberg constant, which is 2.179 times 10 to the minus 18 joules, all right? So that's basically what Bohr came up with, right? Another thing that Bohr mentioned, or he came to the conclusion about, is that in order for an electron to migrate or transition from one orbit to the other, it must acquire energy that allows it to be promoted from, let's say, a lower orbit like n equal 1 to a higher orbit n equal 2, right? So the energy that is acquired by the electron must be equal to the energy difference between these two orbits, right? Also, he said that if an electron is falling from a higher orbit to a lower orbit, then the energy that is the energy difference between those two orbits would be equal to the energy that is emitted by that transition, all right? And that energy would be in the form of electromagnetic radiation, okay? So that's basically his idea. That works very well for the hydrogen atom. In fact, it explains the spectral lines that we observed in the case of the hydrogen gas, right? A very important aspect of this equation here is that there's a negative sign, which we cannot neglect, right? The negative sign basically indicates that there are forces of attraction that exist between the positively charged nucleus and the negatively charged electrons, all right? So that's another important aspect of this equation right here, all right? And as stated here, the energy is zero when the electron is pulled far, 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 infinitely far away from the nucleus. And that makes sense based on this equation here, because if n is equal to infinity, that means that the energy here would be equal to zero. Sorry about that, all right? So that's basically what Bohr is suggesting based on his theoretical work. Now, based on Bohr's work, as I said before, we can explain the line spectra by basically playing around with the initial equation that I showed you. So Here we have the same expression for the Bohr equation. This is for the final orbit of transition. This is for the initial orbit of transition. So to find the energy change for the transition, that would be equal to this right here. Delta E is equal to minus RH over NF squared minus RH over NI squared, all right? And then we can factor out minus RH, and you're going to end up with this equation right here. Minus RH, 1 over NF squared minus 1 over NI squared, right? And we can use this equation here to determine the energy of the transition, right? So if you're transitioning from a higher orbit to a lower orbit or vice versa, then all you have to do is plug in the numbers for the orbits and of course the value for RH here, and that's it. You're going to end up with your delta E value, all right? Okay, now this diagram here basically summarizes the different spectral lines for the hydrogen element, for the hydrogen atom, and as you can see here, you have transitions going from starting from n equals 6, ending up in n equal 1, 5 to 1, 4 to 1, and so on. All these transitions ends in n equal 1, and the radiation produced as a result of those transitions, we call that the Lyman series. And then we have the Balmer series. These are the colors that we actually observe in the line spectra, the one that I showed you earlier, a couple of slides previous to this one, right? So collectively, these are called the Balmer series, and then we have the Paschen series, right? So the Paschen series and the Lyman series, we cannot see with our own eyes. We can observe the Balmer series, all right? So that basically works for the hydrogen atom, all right? Now, before we get to this, I think we could go back to the assignment. Okay, why is it so difficult to see? Let me minimize this here. And okay. Okay, where is... Okay, so now we should be able to do the B part for number 2. So, so the formula that we were just introduced to is E is equal to H nu, right? So just to remind you, E is the energy, H is Planck's constant, which is equal to 6.63 times 10 to the minus 34 joules second. And by the way, let me just say that the unit for H is joules second, right? Students meeting this for the first time, they tend to say joules per second, but that's not true. It's joules second, all right? And nu would be the frequency, all right? So the question is asking, calculate the energy of a single photon of this light. So basically, it's a straight application of this equation. E is equal to H, which is 6.63 times 10 to the minus 34 joules second, multiplied by the frequency. Now, the frequency is what we got earlier. Can somebody remind me? Can somebody remind me of what that frequency was? We calculated it in the A part. Can somebody remind me of what the answer was in A? Oh, let me see. Somebody just answered. 3.84 times 10 to the 14. All right, thank you, Mr. Hernandez. And this would be seconds to the minus 1, right? And then we work this out. So 6.63 times 10 to the minus 34 times 3.84 times 10 to the 14. And according to my calculation, when rounded off to 3 sig figs, it should be 2.55 times 10 to the minus 19 joules. All right? And that's how that is done. Okay. So that's an answer to the B part. Okay? Okay. Any questions about this? Any questions? Any questions? Okay. Let me scroll down to number 3. Okay. Let me clear this. So this question says microwave radiation has a wavelength of 1.0 centimeters. Calculate the frequency and energy of a single photon of radiation. Oh, there's a typo here. Let me scratch this out. Basically, I repeated the sentence below. So let's scratch it out. Okay. So the question is asking for the frequency and energy. So the frequency, they gave you the wavelength, and we know what the speed of light is. So the frequency will be equal to c over lambda. C is always 3.00 times 10 to the 8 meters per second. And then lambda would be 1.0 centimeters. We have to convert that to meters because we have meters here. So centimeter, 1 meter is equal to 100 centimeters, right? So that will cancel with that. Meters will cancel there and there. And then we do the calculation. And that would be 3 times 10 to the 8 divided by 1 divided by 100. And according to my calculation, this works out to be equal to 3.0 times 10 to the 10. And the units here would be s to the minus 1. And that's in answer to the frequency part of the question. And then for the energy part, that would be equal to h nu. We just made this formula, right? H is equal to 6.63 times 10 to the minus 34 joules second multiplied by the frequency, which we just calculated here, which is 3.0 times 10 to the 10 meters, I'm sorry, seconds to the minus 1. And let's see what that gives. So 3.0 times 10 to the 10 times 6.63 times 10 to the 34. And according to my calculation, now this I have to round off to 2 sig figs, which would be 2.0 times 10 to the minus 23 joules, because this will cancel out with this. All right? Okay, any questions about this one? Any questions? Any questions? All right. B part is asking for the energy. So, actually, it's asking for the energy of Avogadro's number of these protons, right? So how do you propose we calculate the energy of Avogadro numbers of these protons? Remember now, this is for each proton, right? So how do we calculate the energy of Avogadro numbers of these protons? Any ideas? Okay, somebody just responded. Any? Oh, I think you mean Mr. Hernandez, NA being Avogadro's number, right? Okay, good. All right. So you're right. So basically, you're going to multiply 6.02 times 10 to the 23 photons by 2.0 times 10 to the minus 23 joules per photon. And that's it. So 2.0 times 10 to the minus 23 multiplied by 6.02 times 10 to the 23. And according to my calculation, when rounded off to 2 sig figs, that becomes 12 joules. And that's how that is done. All right? Okay, any questions about this one? Any questions? Any questions? Okay, let me clear this. I keep doing that. Let me clear this and scroll down to see if there are any questions, any more questions we can do. Okay, let's look at number 4. Number 4 says the primary visible lines from Mercury occur at 404.7 and 435.8 nanometers. All right. And the question is asking for you to calculate the frequencies of these emissions. Okay, now what I'm going to do is I'm just going to calculate the frequency for one of them, and I'm going to leave the other one for you to do on your own. All right. I'm going to focus on the 404.7 nanometers. All right. So again, we're going to use this equation. C is equal to lambda times nu. This time the question is asking for nu. So therefore nu will be equal to C over lambda. And C is equal to 3.00 times 10 to the 8 meters per second divided by the wavelength, which is 404.7 nanometers, and then I multiply that by 1 nanometer, 10 to the minus 9 meters, because we need to convert from nanometers to meters, right? And then we work this out, right? So this will go with that, this will go with that. So let's see what this gives. 3 times 10 to the 8 divided by 404.7 times 10 to the minus 9. And I got, and again, correct me if I'm wrong, but I got 7.41 times 10 to the 14 seconds to the minus 1. All right? And that's that. All right? And basically, you guys would have to do the same calculation. Instead of using 404.7, you're going to use 435.8 here, and then do the same calculation to get the frequency for that wavelength. All right? Okay. Any questions about this? Any questions? Any questions? All right, let me clear this and move on to B. All right, so let me hear what you guys have to say about B. B is asking for you to calculate the energy of the photon in each case, right? So the formula, let me help you out. The formula would be energy is equal to H nu, right? So what would be the numbers you'd put in this equation here? Okay, that's one way of doing it. I never thought of doing it that way, Mr. Hernandez, but that's correct actually, because this is the same thing as HC over lambda. So let's do it your way. So H is what? H is, okay, so what's the value of H? Oh, come on, guys. You guys should know. Okay, so 6.63, I'm rounding it off to 366 times 10 to the minus 34 joules second, multiplied by what's C? 3.00 times 10 to the 8 meters per second divided by the wavelength. And the wavelength is, hold on, 404.7, right? 404.7 nanometers. And what do we need to do next? Okay, convert nanometers to meters. So we're going to put 1 nanometer here, 10 to the minus 9 meters above. That goes with that. This goes with that. This goes with that. And we end up with the final answer. Let me calculate that. 6.63 times 10 to the minus 34 times 3 times 10 to the 8. And then divide that by 404.7 times 10 to the minus 9. And according to my calculation, the answer is 4.9. Let me see, how many sig figs? 3 sig figs. So 4.91 times 10 to the minus 19 joules. All right? And that's how that is done. Now, okay, so this is the way that Mr. Fernandez suggested. What I would have done is I'll take the frequency value from the A part and put it right here, and you should get the same result. So that would be 6.63 times 10 to the minus 34 times, what was the frequency from the first part? Can somebody remind me? What was the frequency from the first part? What was the frequency from the A part? Can somebody look it up and let me know? Okay, 7.36 times 10 to the minus 10 to the 14 or minus 14 or 14, sorry. S to the minus 1, okay? So you should get the same result. Let me just check and make sure. Close. I got doing it this way, I got 4.87, which is close to what we have here. So that's how that works out. All right. Okay. So that's basically how that is done. So let me clear this and move on to the C part. Oh, by the way, hold on. What time is it? Ooh, wait a minute. Oh, it's 12:31. Okay. I guess I have to stop here. All right. Okay, so that's it for today. Let me remind you of the test number 2. That's due, is it tomorrow? I think I have it set for let me check here just to make sure. Oh shoot, what's going on here? Oh, a couple of you have already submitted yours. Yeah, it's due tomorrow. All right, so make sure that you submit it by then. All right. Okay. So that's it for today, folks. we will continue this discussion on Friday. All right? So enjoy the rest of your day. Yes, to answer your question, yes, we're still meeting for STEM Club. So that should be starting right now, actually. All right, so I'm going to